Okay, since the last time I tried this, apparently things cut off and was not so good. So I'm just going to quickly re-explain this one, and I'm not going to show the other one. You have the M plus 3 peak over here at 181. The M is going to be 178. This is your molecular form or molecular weight, not formula. You subtract off the carbons, subtract off the hydrogens, subtract the bromine, subtract the oxygen. I'm just giving you these carbons and hydrogens because I didn't realize that Dr. Hirschauer was doing that. So now I'm giving them to you, right? This gets you this molecular formula. You take this molecular formula and you get a degrees of unsaturation using the equation that Dr. Hirschauer showed you. All right, once you have the degrees of unsaturation, then you come here and you find your functional groups, the bonds that are absorbing there. So C double bond O and also these sp3CHs. Once you have that, then you just draw a molecule that fits the molecular formula and fits the IR data. So I forgot to erase this one, so I'm sorry, I forgot to do that. But this one also fits, right? Any of those where you stick the bromine or the carbons in different places, they all will fit. So any of those will work. All right, for this one, since I have my baby on my lap, it's not as easy to go through the notice whether or not I ran out of space on my iPad. But this one, basically, the first step is what's the mechanism? It's going to be E1, and then draw the mechanism. Bromine leaves, right? You get the carbocation, you get a hydride shift, and then you deprotonate, and you get to your product. RS stereochemistry, only this has stereochemistry, and this is S, this stereocenter right here. It's an S stereocenter, right? This does not have easy stereochemistry in the product. So if I draw the energy diagram for the reaction, it's like reactants. You're going to come up a lot. This is going to be the rate determining step. And it's going to be endothermic to the intermediate. And then it steps down for the carbocation rearrangement, gets the product. But remember, the product has to be higher in energy than the reactant because it's an elimination reaction. What determines the gaining or losing / the control of stereochemistry in the major product of this reaction is carbocation formation. That is what leads to the planar intermediate losing stereochem. That's where you lose the wedges and dashes. If the temperature is decreased to cold temperature, what is the mechanism of the reaction? This is going to be SN1. All right, draw the major product of this reaction. Again, you're going to have the same carbocation from the rearrangement, but then you're going to have, this is water. This right here, and then you're going to have the deprotonated. What determines the gain, losing, or control stereochemistry in the major product? Again, what's controlling the stereochemistry is still carbocation. Planarity, I guess. Planarity. Right, that's still controlling it. Make sure you can see. Oh, you can't see all the way to the bottom. There you go. Carbocation planarity. Bring this down some so that you can see this better. Good. All right. Next problem, answer the question associated with the following question. All right, what's this mechanism of this reaction? So we've got a strong nucleophile, weak base, and we got secondary leaving group. So this is going to be SN2. I know, baby. You want to get out? If you get out, though, you're going to have to come and not complain to Dad while we finish this video. All right. Dad, I got to. Are you okay? You're okay, Dad. SN2, what's the major product? Okay, so if I draw the mechanistic arrows, again, it's going to come to the oxygen, of course. You get to there, right? Because the stereochemistry changes there. Assign RS stereochemistry. This is oxygen, so this is going to be 1, 2, 3. Come around this one. It looks S, but it's actually R. This is going to be 1, 2, 3. It's going to look S, and it's actually going to be S. So it goes from R to S. Draw the energy diagram. This is like one of the easiest energy diagrams you can ever draw for SN2. Reactants, products, it's only one step. Right, it just looks like this. All right, if the carbon on the far right were removed from the reactant, would the rate of the reaction increase, decrease, or stay the same? This would increase because there's less steric bulk, right? If I take this carbon off, so if I use the molecule that it's speaking of, would be this. It's primary now instead of secondary, so you get a faster SN2 because there's less steric bulk. If DMSO was used instead of acetic acid, so if you get rid of this and you change it to DMSO, would the rate of the reaction increase, decrease, or stay the same? It would increase. Remember, the solvent doesn't pick the mechanism, it just picks how fast it goes. So DMSO would increase the rate of the reaction. Good. All right. Answer questions associated with this. So what's this? Secondary strong base, strong nucleophile. So this is E2. Draw the major product. That's going to be, if I just keep this the same way, it's going to be, would it be this, or would it be this? So at first it looks like there's no antiplanar hydrogen at the top, which there isn't, but you can do a bond rotation and you can get one. And remember, these are both two methyl groups, so there's no stereochemistry or EZ in this. So this is the major product. Major. Right, more substituted, major. All right. RS stereochemistry. All right, this is going to be 1, 2, 3. That is S. There's no EZ in this. There is EZ in this one. This one would be Z. But, all right, draw an energy diagram. Again, this is going to be a step up. It's going to be, I guess I'll do reactants, products. And that's it. If the two terminal carbons were bonded together in the reactant, what would be the product of the reaction? So what they're talking about is, if my molecule were this, what would be the product of the reaction? Now, if this were the case, you would get this extra product, right? This would be your product. The new product would it be more stable, less stable, or equal in energy to the original? This would be less stable because it's less substituted. DMSO were used, the reaction rate would increase if DMSO were used instead of ethanol, because it would be, instead of a polar protic solvent, it would be a polar aprotic solvent. Polar aprotic solvent speed up SN2 and E2. All right, that's the last page of this. Thank you.